Everyone. Apparently, the last video that I made on how to use ANOVA didn't go over too well. Hopefully, this one will work out a bit better. Got a bit better wireless connection, and there's not nearly as much background noise right now. So this will be the new video on how to use SPSS to do ANOVA analyses, as well as the non-parametric counterparts for ANOVA. Uh, with ANOVA analysis, a lot of it is exactly the same as the t-test that we did. And in fact, if we use ANOVA to compare two groups, basically we get the exact same answers as we would have uh, if we did a t-test. So what we're going to find is that with ANOVA, we can actually compare more than two groups. T-test is only designed for two groups. And the videos that I'm making for these are actually being used for a couple different classes that I'm teaching. So in one of the classes that I'm teaching, when we talk about the multiple comparisons and how we adjust for that, some of the students have no idea what any of that is about. Um, for the students that I teach at other universities and colleges, they hear me talk about that and are really confused about what the hell am I even talking about? So, because I've got SPSS, we can actually take a look at that and see what it is I'm actually talking about. So let's take a look at some of the assumptions of ANOVA just really quickly, and just to remind ourselves of what we're actually trying to do. So if we have ANOVA, see if I can zoom in a little bit. Hopefully autofocus will work. So if we have our t-tests, and in this case, we have to look at the pooled t-test. This is for two groups. When we look at ANOVA, and it is actually supposed to be all capitalized because it's an acronym for Analysis of Variance. We can look at two plus groups. When we use the pool t-test, we assume that the variance for, say, group A is going to be equal to, or at least similar to, the variance for group B. With ANOVA, we do approximately the same thing, or essentially the same thing, except because we can deal with more than two groups. We're going to have it look more like that. Let's see if I can hit the button on here for autofocus. All right, so that looks a little bit better. The samples that we use in a t-test have to be independent. Samples over here also have to be independent. Samples over here are approximately normal. Samples over here are also approximately normal. Be nice if I could actually spell, right? And equal variances, independence of samples. The samples are approximately normal. How we handle t-test versus ANOVA in, say, SPSS, we can actually take a look at that. But when we're dealing with ANOVA, we have to do our multi-comparison corrections. And we'll actually look at some of the data when we're talking about this. So with the multi-comparison corrections, the ones that we're going to be talking about are essentially Tukey, Bonferroni, and Dunnett. With both of these, you end up having some form of the or the formula, like probability that you get all of your comparisons correct is equal to the probability that you get each pair correct raised to the number of pairs that you're looking at. Here, it's the same thing, but instead we have control versus, say, group A, group B, C, D, and everything else. So just as an example, let's say I'm looking at comparing 5 groups, say A, B, C, D, and E. If I want to look at how many pairs I can make here, AB, AC, AD, and AE, and then BC, BD, BE, CD, and CE, and then DE. So I've got 5 groups I want to test here. Then I've got 4, 3, 2, 1 pairs I'm going to look at it. And if I'm going to be honest, let's say I've only got 4 groups. Well, the first one's going to have 3, second one's going to have 2, the last one's going to have 1. Since we don't have group B at all, that's not even going to be on there. And when we look at these, the Tukey and the Bonferroni, look at all these different comparisons. Done it only looks at the top ones here. So some of the things we need to be worried about are the variances are going to be about the same. They are going to be independent of each other, and they're going to be approximately normally distributed. We're going to look at a couple different data sets and just see how this works. And if you use the appropriate data set, or sorry, if you use the appropriate method to analyze the data, you can actually find that there will be significantly different answers and responses. If everything follows these ideas here, then you can get away with ANOVA. Otherwise, we want to use a non-parametric method. These methods here basically test means. The non-parametric methods, again, these are going to test medians. So if we get these analyses incorrect, weird things can actually happen here. So let's take a look at some of the stuff. So essentially the same ideas apply here as did with the t-test we're talking about last time. So if something doesn't follow the assumptions that we've got for ANOVA, ANOVA is not the appropriate thing to do. And I will say, if you go around any campus and you start looking at some of the research posters that they have, whether it's in say, a psychology department, biology, wherever, a couple of the things that you're going to notice is that a lot of times, even though the research was done by, say, a PhD and a bunch of grad students and all that, and blah, 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 you're going to find that they actually didn't use the right method. So one of the telltale signs that, say, a non-parametric method like we're going to talk about is appropriate versus, well, if I can actually hit the page to put it first, apparently not. We'll try this way. So one of the ways that you can tell if they should be using a non-parametric method versus ANOVA, pretty much everyone's going to use ANOVA because no one really teaches about non-parametric methods because the formulas and all that aren't nearly as nice as they are with ANOVA. And in some cases, some people don't even bother with the multiple comparison corrections and all that. So again, they're even if there should be or could be using ANOVA, they're not using it correctly. So let's take a quick look at what one of the issues is that I'm talking about here. And if you go and like I said, if you look at research on any campus, you're probably going to see some of these issues pop up. And based on some of the stuff that we're about to look at, just know that there can be some significantly huge issues if you don't use the right method. So one of the things that I've seen in a lot of different departments is they will have histograms or bar charts. So let's say we've got group A, we've got group B, and then let's say we've got group C, and you look at the error bars that they have, and then let's say we've got group E. So it's doing, or sorry, I guess that should be C, then D, and then maybe E. If you look at the error here versus the error here, they're not the same. So for data like this, you really should be using some of these non-parametric methods. These two might be fairly similar. This one might be close to these two, but A, B, and E aren't going to be close enough to C and D. So when you see stuff like this, or if you see someone do this and then they talk about ANOVA analysis, they just did the wrong thing, which unfortunately a lot of times can actually make the analyses and everything that they just wrote about in their report somewhere between totally wrong and completely wrong. I know it's horrible, but let's take a look at how some of this data actually comes out. So what I've got, or what I've actually done, is I've got SPSS already up and ready to go. So we're going to look at the practice t-test in ANOVA. This is another data set that I've been working with and playing around with. Takes a moment. Once we know what we actually want to look at, we can see that I've got med A, B, C, D, and E. All right, so that's cool. I'm going to click on OK. And here we have all of our new data. So that's cool. Now, if I want to use the data in a table like this to do ANOVA or the non-parametric method, I have to totally rearrange everything that I've got here. If you're going to be uploading new data, then of course you have to go to File, Open, Data, and then go find it. You will need to change the type of file that you're looking for from SPSS to most likely Excel. So you can see here's where my data is at already. Since I've already got it open, I'm going to stick with what I've got. Now, to do this properly, I'm going to go to variable view and say in column 10, I'm going to type in groups. Column 11, I'm going to type in results. And because SPSS does stupid things from time to time, it doesn't like having a column that's blank, so it just put in this var 00001 or whatever it is. And why did it do that? Because it's SPSS and it insists that you can't have an empty space here. Now, for this analysis, what I'm going to do is I'm going to compare groups A, C, E, and G. For some of the homework, you may have to compare some of these other ones, but the way that we get this done is I'm going to take all the data that I see for medication A, highlight it, do a right mouse click to copy, I'm going to paste it over in results. And then for group, I'm just going to put in group 0 all the way down. I want to look at medication C. So I'm going to copy that. And I'm going to paste that over here. And I'm going to call that group 1. So just type 1 all the way down. So now I've got A, C. I want to do E. So I'm going to copy that. Paste. 2, 2, 2, 2, 2, 2, 2, 2, 2. 2. So A, C, E. And then I'm going to look at G. So again, copy, paste. And then come in here, 3, 3, 3, 3, 3. La-di-da-di-da. And there we go. Now, if we just keep it as is, and we can keep in mind that group 0 is A, 1 is C, 2 is E, and 3 is G, that's totally fine. And just to show us what's going to happen here, going to do this really quickly. So I can go to Analyze, Compare Means and Proportions. Oops. Analyze, Compare Means and Proportions, one-way ANOVA. Click on there. And my dependent list is going to be the results. Groups is going to be the factor. I'm not going to worry about any of this stuff here just yet. I'm going to go ahead and click on OK. And you can see what comes up. It says, according to this, it says that there seems to be a statistically significant difference between at least one of the 4 groups that we're looking at. The stuff that we have down here, honestly, I don't even know what most of this is for, so I'm going to skip that. But if I come back up here, do Analyze, Control or Compare Means and Proportions, again, do a one-way ANOVA. And this time I'm going to do a post hoc test. So here we can look at what I was talking about. There's Tukey, there's Bonferroni, and there's Dunnett. I'm just going to click on Tukey just because. Click on Continue, click on OK. And now we get into all of this stuff down here about doing multiple comparisons, and you can see that we have group 0 versus 1, 0 versus 2. I wish that wouldn't come up like that. 0 versus 3, 1 versus 0, 1 versus 2, 1 versus 3, and so on. And we can see that it looks like there seems to be a statistically significant difference between group 0 and group 3 based on the significance level here. If we're looking at 1 versus 2 and 3, looks like groups 1 and 3 seem to be, again, statistically significantly different from each other. Looking at 2 and 3, looks like it's just right on the borderline. And looking at the confidence interval over here, it looks like this is going to come out to be 0.050 something something or 0.0 something something because we've got a negative value to positive value. When we look at group 3 versus everything else, you can see that basically, yeah, it does look like it is statistically significantly different from everything. I can even scroll down here. And one of the weird things is here, this is trying to tell us that groups 2 and 3 look like they belong in the same group. And then 0, 1, or 1, 0, and 2 also belong in the same group. For a class like this, again, you can look at all these groups. And if you remember that group 0 is A, 1 is C, 2 is E, 3 is G. All right, cool. If you want to do this a little bit more professionally, which I think is what most of us should actually be doing, I can go to Variable View. And I can come up here to where it says Values when we're looking at these groups. Click on there. I'm going to click on Add. I'm going to say 0. And that's going to be medication A. value of 1, medication C, value of 2, medication E, and 3, medication G. So now if I make those changes here, I can click on OK. You can see that this changed here. When I look at the data view, it's done absolutely nothing here. But if I go back up again to analyze, compare means and proportions, and then one-way ANOVA to keep everything else the same as I had before, click on OK. Now you can see that all the names have actually changed here so that you don't have to memorize what are all of these different groups. It's just right freaking there. Okay. So now that we've made that small change, let's try to do this for. So again, I'm going to go to Analyze, compare means and proportions. Means and proportions come down to one-way ANOVA. Contrasts. These can actually be kind of useful if you need them. Let's say you wanted to compare groups A and C versus B and D or something like that. That's what these contrasts are for. We're not doing that here because if you need to do that, there are a lot better ways to actually do it than this. So I can go to post hoc. And we talked about Tukey. Now said Bonferroni and done it. So with this done it, you can see that we're going to have our control category. I can either call it the first or the last. It doesn't really matter. There are some things down here for when equal variances are not assumed. I'm not going to worry about any of these for a couple of reasons. Basically, I don't know what any of them actually do. So I'm going to leave them alone. So I can click on continue. I'm going to come up here to options. And now when you're looking at all of these, we can look at descriptive data for everything we have. Homogeneity of variance test, that's kind of important for ANOVA. Welch test, that's another version of the homogeneity test, I believe. We can do the mean plots. So click on all of that stuff and click on continue. Bootstrap, we're not going to worry about that all that much. But here I'm just going to go ahead and click on OK. And ANOVA comes in, does all my analyses over again. And when you look at all the different means, you can see what the mean of each one of the groups are, the standard deviation. You can see that the standard deviation for group G is about 15.5, whereas the rest of these are like between 9 and 10. So perhaps G, if we had more data, might actually show that it's a kind of statistically significantly different with the variance. When we look at the homogeneity of the variances, the significance here is low, but not below, say, 0.1 or 0.05. Just going to say again, if we have small data sets like these, so 10, 15 people in each group, I would probably actually use a significance level of 0.1 instead of 0.05, just because our data size is so small. And then we come down here. So robust test for equality of means. This is telling us that it definitely does look like there's a statistically significant difference between groups. So cool. And now we look at the Tukey AHD, HSD, Bonferroni, and the Dunnett. If you notice, with all of these, the standard error is essentially the same all the way down. So when we typically do a two sample, or a lot of times when we do the confidence interval, we're actually going to be dealing with say the mean, or in the case of this, the mean difference plus and minus some t value times that standard error. Because of all the data points we have, that t should be, say, about 2.1. We can see the standard error is approximately 5.066. So I'm just going to call it 5 here. If we try to make this a little bit easier to deal with, we would say this is plus or minus 2 times 5. So our approximate 95% confidence interval is going to be that mean difference plus and minus 2 times 5. So about plus or minus 10. So if we were to look at the Tukey HSD for medication A versus medication C, we can see that this is about a 4.5 difference, plus or minus 10. So this will give us 4.5 minus 10. So negative 5.5 to 4.5 plus 10 to 14.5. And if we look at what we have up here, just because of the way that these are actually calculated, you can see the mean difference here is taking group A and subtracting group C, the values that we get. And what we should be seeing using the reverse formula is this should be about 5.5 here. This should be about negative 14.5 here. So you can see that these are a whole lot larger than we would have thought, which means that we've got that mean difference plus and minus some t value times 5. And if we, again, look at that and say 4.5 plus and minus some t value times 5, looking at the data that we've got there, we know that if we look at 18.1 minus 14.5, we're going to get, I don't know, some number. So I don't make too big of a fool of myself here. I'm going to go ahead and or try to do this with the graphing calculator. And since I'm going to be doing it with the graphing calculator, can actually use all the correct values. So let's take a look at what are all of those correct values again. So we've got here negative 4.47, and we've got a negative 18, 0.1187. So negative 18.1187. And that's going to be the low end. And we are going to basically subtract a negative value, 4.47233. And you can see that our margin of error is actually going to be 13.6464 approximately. So if we look at divide that by the 5.06693, we see that the t value used is actually about 2.69, as opposed to the 2.1 if it was just a standard t-test. So that's one of the issues that's coming up. If we try to do that again with the Bonferroni test, Looking at, say, so we did medication A versus C here. Looking at medication A versus C, we can see what the confidence interval is here. It's negative 18.6190. Up here, it's negative 18.1187. So again, we're going to get that really large, like 2.7 something t-value. Again, coming down here, 16.8971. So we do 16. Try and get all of this on the screen all at once. So hopefully we can see everything. So 16.8971 minus the difference, 4.47233. Now we divide that by the 5.06693. And we can see that for the Dunnett test, where we're only making 3 pairs versus 6 pairs, the t-values that we use are going to be extremely, or quite a bit different. And that's because of the formula that we were looking at. So even though on SPSS, it's telling us that this is the 95% confidence interval, that's based on probability that you get them all correct is going to be equal to, say, 0.95, which is going to be equal to the probability that you get each pair correct raised to the number of pairs. So if it's a Tukey or Bonferroni, we end up with the data that we have anyway. We're going to be making 6 comparisons. So 9 or 0.95 raised to the 1/6 power is equal to the power or probability that we get this pair correct. So what is that? So 0.95 raised to the 1 divided by 6 power. So it's actually given us the 0.9915, 99.15% t-value, as opposed to the 95%. So this is part of the reason why we need to do these multiple comparisons here. If we don't do it, we can very easily be taken to a weird place. Now, I'm going to go back one more time. Oops. Wrong button there. And I'm going to add one more group. So I'm going to add on group H. So come down here, paste that. I'm going to call this 4. I'm going to go to variable name, and now have to add one more. So group 4 is now medication H, as opposed to preparation H, which is a totally different thing here. So click on OK, and things are done. Go back to data view, go back to analyze, go back to compare means and proportions, one-way ANOVA. Everything else is already set up. And now we're looking at everything here. And it's telling us that we've got all these different means, all these different standard deviations. Our tests for homogeneity of variances are all telling us that there does in fact seem to be a statistically significant difference. in the variance of our different groups here. And you can kind of see here going from standard deviation 3 to 16, kind of a big jump there. This right here is telling us that everything we are about to look at using ANOVA is actually an inappropriate thing to do. Scroll down here. Still telling us that there's a statistically significant effect. And now if we look at the confidence interval here, and even look at the standard error here, we notice that the standard error here is now 4.56, whereas before it was, what was it? 5.66. So that standard error is basically the average error or average standard deviation from all of these, because this one is so much smaller than everything else. That's why the value down here has changed. But what you're actually going to find again is when you try to do the calculate the t-values here, they're actually going to be a little bit larger than what we did before, because we're now looking at 5 groups. And we can look here and see that there does in fact seem to be a difference between all 5 of the groups. G seems to be really low. C seems to be the highest, and we already know that H has the smallest standard deviation. So now that we've got all of that done, and we're now basically told that ANOVA does not work, I can go to Analyze, go to Non-parametric tests, go to Independent samples, click on that. We want to compare medians across groups. Go up to Fields. The groups that we want are what we had before. The results go into the test field. Settings here. We can customize test or automatically choose the best test for the data. If you look, because we already chose that we want to look at medians, it's telling us we have to customize the test. That would mean the Acruscal-Wallace test that we've got here. And we can do these multiple comparisons, so we can look at all pairwise, none, or whatever. So we're going to look at all the different pairwise tests here. If you look at Mann-Whitney, Kolmogorov-Smirnov, and this other one here, it's only for 2 samples. Sometimes we can do a test for ordered alternatives if we're dealing with data where rank is involved. Something like that might be actually kind of useful. So estimate confidence intervals across groups. Again, that's for 2 samples. We basically have K samples, so where it says here, compare medians across groups. That's what we want to do. We can go to test options. Again, even though we're now looking at 5 different groups, I would actually be tempted to change the significance level and confidence level that we want to look at. User missing values. This isn't really anything we need to worry about. I'm going to go ahead and click on Run. And it's going to take a moment to try to do all these calculations. Now that that's done, we can scroll down here. And SPSS is already trying to do a couple different things here. So it's looking at the medians of results are the same across categories of groups. It's giving us our significance level. And it's already telling us here, reject the null hypothesis. That's telling us that the medians for all these different groups are in fact different from each other, or at least some of them are. Then here it says the distribution of results is the same across the groups. So another test there. This is telling us that it's statistically significant. So again, reject the null hypothesis. So this is telling us that the groups seem to be different from each other in their medians. And this is telling us that the groups seem to be different from each other based on the distribution. So the standard error that we're looking at, potentially even some data being from, say, normal distribution, and some data being from some other distribution that's not normal. So those are a couple possibilities there. We can then scroll down, get a really nice box plot of what's going on. So you can definitely see medication H has a really small range, medication G has a really large range. That's telling you what's going on there. And then looking at all of this, it's actually telling us that there only seems to be one group out of everything that we're looking at that seems to be statistically significantly different, and that's group H, their medication H versus medication C. So you can definitely see medication H, everything is basically below this median value here. And with medication E or C, everything seems to be basically above that median group. So that's going to be the only comparison that actually comes up as being statistically significant. And then you can see here that they have some of these other things, significance and then adjusted significance. So you can see here it says significant values have been adjusted by the Bonferroni correction for multiple tests. So this is the one that you would actually want to look at. And when we look at the data, and for whatever reason, when we look at 5 data points, SPSS actually puts the star in here inside of a pentagon, and then it tries to tell you with the color coding that's here. You can see that we've got the blue here, which means that the p-value is small enough. It's telling us that C and H seem to be statistically significantly different from each other, but pretty much everything else is all the same. Uh, so Kruskal-Wallis test, don't know if we need that, or the results from that anyway. But it does seem to be telling us that there seems to be a significant difference. Again, looking at the data, we can see where that's at. And a comparison of the groups. So again, we want to look at the adjusted stuff here. This is now saying G versus C seems to be significantly different, and H versus C seems to be close to being significantly different. Again, because we have such small data sets, I would probably actually go with a 0.1 or 90% confidence interval for these. So this is telling us that using a different version of the test, they're actually two different groups that are different from each other. And then here it's just looking at all the data put together. Does it look normally distributed, low at the edges, high in the middle? Yeah. But does it look like it's a bit skewed? Yes, it does. So this is telling us that using the non-parametric test is better. And this is just telling us that, hey, we've got 10 data points in each one of the groups. So one other thing we can do with the data, and other thing that might actually get in a little bit of trouble for, but hey, never been one to shy away from getting in trouble, especially if we can have or do proper data analysis on it. Well, let's get rid of that. What I've got, oops, let's make it all go away, right? So what I've got here are presidential jobs numbers. These go all the way back to January of 2001 and go through month by month, all the way up to July of 2024. And for whatever reason, you can see that it only uses 4 letters in each president's name. There should be all 5 in there. I can go in and we're going to do a quick ANOVA analysis on this. So variable view, uh, number of the president. So if it's a 0, that's actually going to be President Bush, uh, Jr., I should say. If it's a 1, it's Obama. 2, it's President Trump. And 3, President Biden. And looking at the data, I'm actually wondering if I already. So one of the things that I did with this data is if you look here, we're going from 2019 all the way into 2022. So I've already eliminated all the data in 2020 and 2021. Part of the reason is if we included that data in 2020, when Trump was still president, we had some major losses of jobs and everything else. And in general, uh, they weren't because of any particular policy that he had. It was just because of the pandemic. Then in 2021, uh, Biden picked up a lot of those jobs that were cut because we're basically coming out of the pandemic at that point and kind of had an idea of what was going to be going on. So because those 2 years are very, well, exceedingly skew the data one way or the other, I got rid of them. If I included them in here, when we look at the results, it exacerbates some of the analyses that we can do here. But I'm going to go to Analyze, compare means and proportions, and the one-way ANOVA. The dependent list is going to be the number of jobs that are created in any given month. And each one of these should be multiplied by 1,000. So in April 2019, there were 308,000 jobs. Number of president, that's going to be the factor. Post hoc, again, Tukey, we can do done it. And if we want to compare everyone against, say, George Bush, we can do that here. Want to compare everyone against Biden, we can do that here. And for might as well leave it like that, just to have some fun. And then options, descriptives, homogeneity of variance, mean plots. So if you think about job creation under Trump, under Biden, under Obama, and under George Bush, 2 of those presidents were Republican, 2 of them were Democrat. And if you think about any of the commercials that came out, you'll know that a lot of times the Republicans would complain that the Democrats had a lot of job killing uh, ideas and the economy was really bad because of it, and there weren't people were losing jobs and all that sort of stuff. With what we're about to do here, we can actually get an idea, maybe anyway, whether or not any of that is actually true or false. So if I go ahead and click on OK, it's going to take a moment to analyze everything. And then we look at the data here, and you can see that on average per month when George Bush Jr. Was in office, there were about 22,000 jobs made per month. Obama, 110,000. Under Trump, 177,000. Under Biden, about 300,000. So just looking at Bush versus Obama, Obama was a whole lot better than Bush. Trump seems to be a bit better than Obama was. when we look at the multiple comparisons and everything else, we have to try to figure out, are these actually true or not? But looking at the test of homogeneity of variances here, this is telling us that there does seem to be some issues with the standard errors or the variance for all the different precedents that we've got here. So that's telling us that ANOVA is not the appropriate thing to do here. But let's say we take a look at it anyway and see what comes up if we do the wrong thing. And if we look at, and this is again doing an inappropriate analysis here, you can see that when we look at George Bush versus Obama, Trump, and the Biden, George Bush has all of these dismal average numbers compared to each other or compared to the other three presidents. When we look at Obama versus Bush, you can see that Obama had about 88,000 more jobs per month created than George Bush did. When you look at Obama versus Trump, you can see that Trump had about 67,000 more jobs per month than Obama did. However, there doesn't seem to be a statistically significant difference there. And then looking at Biden, Biden seemed to do a lot better job than Obama did. Come down here to Biden, and this is telling us that Biden basically beat Bush, Biden beat Obama, and then Biden and Trump. Even though Biden had 110,000 jobs more per month on average, because of the huge standard error, we can't really say that there's a statistically significant difference going on there. Same thing down here with the Dunnett. And we can look at how some of these groups seem to compare to each other, which is kind of weird. Looking at the 4 presidents in a row, you can see that there seems to be a bit of a trend going on there. But again, because the data saying that we don't have equal variance between the groups, that ANOVA stuff, even though we could, a lot of times you will actually see people use that anyways, it's not the appropriate thing to do. So we're going to go to the non-parametric test, independent samples. We're going to compare medians across the groups. The number of the president, that's the group. Jobs is going to be the test. Excuse me, the test field. So objective, we've got that field. Settings. We want to do the Kruskal-Wallis and compare medians across the groups. Test options. We've got quite a bit of data here, so I'm completely fine going with 0.05. Now I can click on the run button here. It's going to take a moment. Now that that's over with, this is telling us that there does in fact seem to be a huge difference between the medians of job creation for each of the presidents. And it also tells us that there seems to be a difference in the distribution of the presidents. So this one here is basically telling us again that the ANOVA test that we looked at before is not correct. Scrolling down here, looking at the data again, we can see the box plots for everything. And then scrolling down even further, we can see Bush versus Obama. That seems to be statistically significant. Bush versus Trump seems to be significant. Bush versus Biden also seems to be statistically significant. Obama versus Trump, though, now all of a sudden this is showing that it's doesn't seem to be statistically significant. And Trump versus Biden seems to be showing that there is. a statistically significant difference going on here. And when you look at the results here, you can see the median for Biden versus the median for Trump. And using the more appropriate method, so non-parametric Kruskal-Wallis test, that's basically suggesting that Biden is better than Trump was. Looking at all the data here, there doesn't seem to be much of a difference between Obama versus Trump, but there does seem to be a statistically significant difference between all the other comparisons we can make here, which I think is kind of interesting. And then look at the data. So again, box plots, looking at another comparison here, using a little bit different methodology. Here, the adjusted significance is saying that maybe there isn't that big a difference between Trump and Biden. So we can kind of see that here. So again, depending on the method you use, you can actually take the exact same data, run it through what seems like it should be the exact same analysis, and you can actually come up with very, very, very different statistically significant results. And just going to be honest, this sort of stuff happens quite often. Some of the things that you can actually do when you're dealing with data like these, when you have results that are kind of inconsistent, like we just saw, you can get a little bit deeper into, say, the theory behind all of these different tests. And you might find that theory behind one of the tests is kind of violated by the data that you're looking at, or however it happens to be. And I actually cut some of the data out, as I said, looking at Trump and Biden. If I kept that in there, then Biden would have been significantly different than Trump and basically beaten him very, very badly, because was a month or two when there were like 500,000 jobs that were lost. And that was during Trump's presidency. But basically, what we just looked at there, looking at actual factual numbers up until the point when I stopped looking at them, you can kind of get the idea that maybe some of the ads that were being put out by Republicans just weren't true. If Democrats were putting forward ideas that were truly harming job creation and all that, then you should have seen George Bush and you should have seen President Trump, huge numbers. But that didn't happen. Is there some other stuff we could do here for the analysis? As far as a one-way ANOVA, no. However, we could add a couple different variables in there, and we could look at, say, who or what political party was in control of, say, the House of Representatives, what political party was in the control of, say, the Senate at the time, as well as whoever the president was. To do that, we have to use a little bit different methodology, but it's basically ANOVA for, instead of comparing one set of factors, in this case, president, you can test it against 3 different factors. And to be honest with you, how do you do that with SPSS? It's actually been a while since I've had to do that, so I don't remember all that well. So, but that is something that you can look at. And all the data that I just showed you there, I basically just went to Google and typed in job creation numbers by month, and all that data came up off of one of the government websites. So it's in a little bit different order, because what they ended up doing was I believe across the screen it was years. It was like 2001, 2002, 2003, 4, so on. And then January, February, March, April, all the way through. So it took me some time to take that data and put it in. And the last time that I did it was back in like September. So I don't even have all of 2024's data. But if I did collect that new data and look at it, would that change any of the analyses that we did? Would that make some of the conclusions that we had between, say, Trump and Biden for the different data sets? Would that make a big change? Maybe, maybe not. If you're interested in doing that, go ahead and again Google job creation numbers by month and look at National Institute of what is it? National Bureau of Employment or something like that. Uh, I would have loved to try to do that for you live, but the last time that I tried to do that, Google decided to use different, or looking at different websites, and it took me 30 minutes just to find it. So I'm just going to say you can find it if you want to. With that said, I'm hoping that this ANOVA thing is actually going to be a bit more useful for everyone. And hopefully the audio on this is a whole lot better as well. So look forward to torturing you all later. Bye.